Hi there, welcome to this video. My name is John. I provide mathematics tuition for A-level maths, A-level further maths, including 6-term examination papers and mathematics admissions tests. Very warm welcome to this video where we're going to take a look at the normal distribution. So, just a word of warning. This is going to be quite a long video and it's going to be using certain techniques that you don't normally come across at A-level. So it is going to go kind of beyond the A-level specification to a certain extent. And this is deliberate because, first of all, to really explain some of the details of the normal distribution, we need to go a little bit beyond the typical A-level content. But also it's to potentially introduce you to ideas that you might not have come across before. So personally, when I was doing my A-level maths, I liked this. I liked being introduced to new ideas in mathematics and being able to go away and find out about them. So I remember, for example, my teacher sometimes mentioning things like vector spaces when I was doing my A-level maths, and I didn't know what a vector space was, but I went away and I found out about it and I thought it was interesting. And that was something that I enjoyed doing in mathematics, doing some independent research and independent learning. So what I hope is that some of you watching this video will also appreciate doing things like this. If you don't want to go beyond the specification material for your A-level maths, don't watch this video. Okay, there's going to be quite a bit of stuff in this video which is going to go a little bit beyond. But it is stuff that if you want to understand it, you can. It's not beyond your reach to understand it well enough, at least to understand this video. Nevertheless, if you do have any questions about anything that I mentioned, because I'm not going to go through all of the details, it's not going to be a fully comprehensive video of every single detail. If there is anything that I don't explain particularly well or don't explain in a way that you understand, just ask the question, what you need clarification on. Ask in the comments section, get in touch or whatever. If there is anything that I mention, because I'll be talking about double integrals, for example, and integrals in polar coordinates, if you want me to make a video on this stuff further down the line, then just let me know. I'm always open to ideas for new videos, and my aim really is to help you as much as possible to prepare for your A-level maths exams and to encourage you to learn more about mathematics, especially if you are looking to go on to do high-level mathematics. You know, thinking about what I used to enjoy doing at A-level, I'm trying to target that kind of person. Okay, so what we're going to be having a look at here in this video are some of the properties of normal distributions that at A-level typically you will just be told and expected to take for granted, take as given. We're going to be analysing the normal distribution in a bit more detail in this video. Okay, so some of the things you will already know to a certain extent. But as is usually the case for mathematics, we really need to kind of look beneath the surface or peer behind the curtain, see what's going on behind the scenes to really fully understand why things are the way that they are. So that's what I hope to do in this video, to kind of highlight some of the reasons why things are the way that they are. Okay, so what we're going to do first of all is to consider the function, because the normal distribution has what's called a probability density function, and that is just a function in the normal sense. Okay, so initially we're not going to use the phrase probability density function because there's some things that we need to check before we can ascertain whether the function that we're dealing with is actually a probability density function. Okay, so we're going to be going through this in quite some detail. So we're going to consider the function f of x. And you'll have to bear with me in this video because there is quite a bit for me to write at various times. So it's going to be quite a long video. So f of x is equal to 1 over the square root of 2 pi sigma squared e to the minus a half x minus mu over sigma squared. Okay, so yeah. Okay, where mu and sigma are constants. Okay, when we finally show that f of x is actually a probability density function, we will be able to refer to mu and sigma as parameters. Okay, but that's what we need to show. We need to show that f of x is actually a probability density function. Well, actually, we're going to take a slightly simpler version, first of all. We're going to take g of z, which is 1 over square root of 2 pi e to the minus a half z squared. Yeah, that's it. Okay, so this is it's from the same family as f of x. Okay, it's from the same family of functions, but here we've got effectively mu is equal to 0 and sigma is equal to 1. Okay, actually it's really sigma squared. I'm gonna write sigma squared here. Okay, and sigma, another restriction on sigma, by the way, is that sigma is going to have to be greater than 0. Okay, so what do we mean by probability density function then? So a function is so conditions for a PDF. So probability density function. Okay, there's a few conditions. So one is, I'm going to say it has to be continuous because we're interested in continuous random variables here. Okay, a probability density function is something that we use to model a continuous random variable. I'm going to say that we need the function to be continuous. This is not quite right. So there might be some of you watching this that will know perfectly well that you don't strictly need continuity, full continuity. You can have discontinuities at certain, as long as they occur in a certain way in your PDF. But I don't want to get too bogged down in details. Even though we're going to be going into quite a bit of detail here, I'm not going to get too bogged down with details. So we're going to have continuous. Our function needs to be continuous. If I remember rightly, really it has to be right continuous. So it has to be continuous at each point. At each point. Okay. So like I say, yes, I'm aware it doesn't actually have to be continuous. It just has to be, I think it's right continuous, if I remember rightly. But anyway, beside the point. So conditions for a PDF, our function has to be greater than or equal to 0. In fact, I'll tell you what. F of x has to be greater than or equal to 0 for all x. And the integral from minus infinity to infinity of f of x dx has to be equal to 1. Okay, so these last two conditions, why do we need them? Well, we're going to use our probability density function to calculate probabilities. So the probability density function doesn't give us probabilities, it gives us probability densities. And from these probability densities, we can calculate probabilities. Okay, using integration, if it's a continuous random variable. Now, if we've got a discrete random variable, so you've come across discrete probability distributions, such as binomial distribution, for example. This has a probability mass function which works in a slightly different way, and rather than using integration, you'd use summations to calculate probabilities from a probability mass function. And you can get kind of hybrid functions as well. random variables that are kind of part continuous, part discrete. Again, we're not going to worry about stuff like that. But with a continuous function, we calculate probabilities using integration. Now, probabilities are always between 0 and 1, inclusive, okay? Including 0 and 1. But no probability is less than 0, and no probability is going to be greater than 0. So by insisting on our function being non-negative for all x, we can guarantee that any probability that we calculate on the basis of f of x is going to be non-negative, okay? And similarly, the integral from minus infinity to infinity of f of x dx equals 1. That guarantees that any probability that we calculate based on f of x is not going to exceed 1. So these two conditions kind of trap all of our probabilities in the right range, between 0 and 1, including possibly 0 and 1. Okay? So that's why we need those conditions. So they're the conditions that we're gonna aim for. So let's take our function f of x. So remember, f of x was equal to 1 over the square root of 2 pi sigma squared e to the minus a half x minus mu over sigma squared. This is continuous. Obviously, we're not in this going to be proving that in a properly formal way, but it's continuous. Okay. It's great. The value of f of x is always greater than or equal to 0. The kind of the beef of this function is here in this exponential. This is an exponential function, by the way. Maybe I should have made that clear. This e, it's the exponential function. And the exponential function, as you know, is always non-negative. In fact, it's always greater than 0 for any finite value of x. So we've always got that f of x is greater than or equal to 0. Okay, so we can tick off both of these two properties. But what about this third property, the integral from minus infinity to infinity of f of x dx is equal to 1? This is a little bit trickier. It's a little bit trickier to calculate. So this is where we're going to be going a little bit beyond A level. We're going to be getting into double integrals, and we're going to be getting into integrals of using polar coordinates. Okay, so let's have a look how we're going to do this. So we're actually going to take what I wrote as g of x earlier, which was I said it was of the same, from the same family, from the same kind of exponential normal family of functions. We're going to consider that one instead. So we're going to have a look at the integral from minus infinity to infinity of, I'm going to miss off the 1 over square root of 2 pi, e to the minus a half. And what I'm going to write here is x squared plus y squared dx. Actually, I've missed off an integral because we're doing a double integral here. We're going to consider this integral. Okay, so remember g of x was 1 over the square root of 2 pi e to the minus a half x squared. I wrote it as gz before. It doesn't make any difference. Gx, gz, whatever. Okay, so you'll see why in a second why I've started with this double integral. Okay, now I'm going to have to miss out some of the details with this. Because double integrals can be a little bit fiddly from time to time. There's certain things that I'm going to do here which I can only do because of the certain features that this integral is going to have, certain nice features. But double integration was something that, again, going back to when I did A-level further maths, I was kind of I latched onto this idea, double integration, and it kind of fascinated me at the time. Don't be scared of doing your own research and doing a bit of independent learning and things like that. Okay, so this is equal to minus infinity to infinity of the integral from minus infinity to infinity e to the minus a half x squared times e to the minus a half y squared dx dy. Okay, so all I've done here is basically use laws of indices. Okay, to split up the e to the minus a half x squared plus y squared into e to the minus a half x squared times e to the minus a half y squared. So this is equal to, okay, a little exclamation mark here, because this is something that we can do here just because of the particular function that we're trying to integrate. Okay, so what we get is the integral from minus infinity to infinity of e to the minus a half x squared dx times the integral from minus infinity to infinity of e to the minus a half y squared dy. Okay, so okay, bear this in mind as well, that the integral of, let's say I've got h of x dx, the x here is what's called a dummy variable. Okay, it's not a real variable as such. In fact, if you read one of my favourite books, Principia Mathematica, Bertrand Russell and Alfred Whitehead, they talk about integrals in there, and they actually refer to the x, what I've highlighted here, as an apparent variable. It's not a real variable, an apparent variable. Okay, what that means is basically it doesn't matter which symbol I use. Okay, so I could write, for example, the integral of h of, I've just written x just through force of habit there, h of t dt, or the integral of h of whatever this symbol is, d with respect to that symbol. Okay, as long as there's agreement between the two symbols here, then it doesn't matter which symbol I use. So using that idea, I can replace this y and this y with x's. Or I could replace the x's in the other one with y's. It doesn't make any difference. So I get that. Which therefore, if you notice, both of these integrals now, this one and this one, are identical. So what I get is the integral from minus infinity to infinity of e to the minus a half x squared dx, all squared. Why are we doing this? Well, the reason is because of this thing here, e to the minus a half x squared, can't be integrated in an analytic sense. So what I mean is, there's no function. So there's no function f of x that when I differentiate this, at least not in a closed form, d by dx of f of x is equal to e to the minus a half x squared, for example. Okay, no such function exists in a closed form. So that means that it kind of prevents me from using the normal techniques of integration. And that's why I'm going to all of this hassle, all of this trouble, to try to calculate this integral. But notice that this is what we related to what we were calling g of x earlier. It's not the g of x because I've missed off the 1 over square root of 2 pi. We'll come to that. We'll sort that out. Don't worry. Okay, but that's why we're going to this, all this trouble. Okay, so let me get rid of that. We don't need that anymore. Let's get rid of this. Right, so now we're just going to have to change track. I might have to go into a new page, actually. Oh, I've got enough space, I think. Okay, so going back to... So, to be continued. We're going to have to come back to that. So, we're going to go back now to the integral from minus infinity to infinity of the integral from minus infinity to infinity of e to the minus a half x squared plus y squared dx dy. This can be written in another form using polar coordinates. Not polar coordinates. Yeah, polar coordinates. Sorry. I was thinking spherical coordinates there. No, polar coordinates. And a little exclamation mark over this, because this is something that I'm not going to be explaining here. It's something that maybe, if you want me to make a video on this further down the line, just let me know, okay? But I'm not going to explain it in this, because otherwise the video is going to end up 5 hours long. And it's getting late. Okay, so this is the integral from 0 to infinity of the integral from 0 to 2 pi of r e to the minus a half r squared d theta dr. Okay, so this is called polar coordinates. Okay, some of you might have come across polar coordinates if you do further maths, for example, you might have come across polar coordinates, but and you do integration with polar coordinates, but you tend to do just single integrals as opposed to double integrals. Okay, so we can evaluate this. This is actually something that we can evaluate. Well, actually, we need to split it up first. We can write it as the integral from 0 to infinity of r e to the minus a half r squared dr times the integral from 0 to 2 pi of d theta. Okay, so this thing we can integrate. Okay, whereas we can't integrate, if we just had e to the minus a half r squared, we wouldn't be able to integrate that. But because we've got the r in front of it, we can integrate it. So if we think about, if we use, there's various names. You can use integration by substitution here, or some of you have probably heard it called something like reverse chain rule. I hate calling it reverse chain rule. It just doesn't make sense to me why it's called reverse chain rule. I just don't like it. I call it integration by knowing what you're doing, because that's what it is. It's by you're spotting a pattern and you're taking advantage of that. Whatever you call it, anyway, you can use that integration technique to integrate this thing. So let's take a guess. Let's take minus e to the minus a half r squared. When I differentiate that with respect to r, what do I get? I get minus r e to the minus a half r squared. So this then is going to integrate to minus e to the minus a half r squared between 0 and infinity times the integral of theta, times theta between 0 and 2 pi. Okay, so this is equal to, plug in r equals infinity, you're going to get 0. Plug in r equals 0, you're going to get minus e to the 0, which is just 1. So you're going to get minus 1 times 2 pi minus 0, which is equal to 0 minus minus 1, just 1, 2 pi minus 0, 2 pi. Okay, so let's go back now to our to be continued. Because what this shows us is that our original integral is equal to 2 pi. But this double integral that I started with here when I changed it into polar coordinates is also the same integral that I started with before, namely this integral, which I showed separately to be equal to an integral from minus infinity to infinity of e to the minus a half x squared dx all squared. Okay. By the way, this is called the Gaussian integral. This. So let's get rid of our TBC. So that is equal to 2 pi. Perfect. So let me go into a new page. So what that means is then, by the way, it might be a good idea for you to take notes if you need to with this video, so I can't keep everything on the screen all at the same time. The integral from minus infinity to infinity of e to the minus a half x squared dx is equal to square root of 2 pi. So, therefore, this implies, and it's not very often that I use this symbol actually, the integral from minus infinity to infinity of 1 over square root of 2 pi e to the minus a half x squared dx is equal to 1. Okay, and this was g of x. Right from the very start. What I call g of x. So what we've shown here is that g of x is a probability density function. Okay, g of x is a PDF. Why? Because it satisfies all of the conditions. It's continuous, it's non-negative, and the integral from minus infinity to infinity of g of x dx is equal to 1. But g of x is not f of x. Okay, so we're not quite done yet. So now we need to have a look at the integral from minus infinity to infinity of f of x, which was 1 over the square root of 2 pi sigma squared e to the minus a half x minus mu over sigma squared dx. Actually, we don't really need to go through all of that business again, because what we can do is just make a substitution here. We can make the substitution z equals x minus mu over sigma, use integration by substitution, and what we get is that this is equal to the integral from minus infinity to infinity of 1 over the square root of 2 pi e to the minus a half z squared dz, which is, as we've already seen, equal to 1. Okay, so the integral of f of x from minus infinity to infinity of f of x dx is equal to 1. Therefore, f of x is a probability density function. Okay, so f of x is called a normal probability density function. Okay, and g of x is called the standard normal PDF. Okay, so the standard normal PDF is just a special case of the general normal PDF. Okay, so now that we know that f of x and g of x are both probability distributions, we can start to use them to model random variables, continuous random variables. So if x is a continuous random variable with a normal, it follows a normal distribution, then we can say x is distributed. So we use this little twiddle symbol. You've probably seen it before. Distributed normally, and now we specify what are called the parameters of the normal distribution, which are mu and sigma squared. So the parameters uniquely specify a particular normal distribution. Okay, so if I tell you I'm thinking of a normal distribution and its parameters are this value for mu and that value for sigma squared, then you can determine exactly which normal distribution I've got in mind and which normal distribution I'm talking about. Okay, the normal family of normal distributions are an example of what are called location scale distributions. Just so you know, the location parameter is mu and the scale parameter is sigma squared. Okay, so let's say we've got another random variable which follows a standard normal distribution. This often has its own notation. Okay, z. So whenever you see z as being used as a symbol to represent a random variable, now obviously this depends on the context, the specific context, but very, very often, although not necessarily always, very often, that will indicate that the random variable has a standard normal distribution. Now, this is not always the case. You do have to pay attention to the context, but it's very common to, if a particular random variable has a standard normal distribution, it's very common to use Z to represent that random variable, although not always. Don't take it as something that has to happen, because it doesn't. So Z is distributed normally with parameters, in this case 0, and I'm going to write it as 1 squared. I know 1 squared is equal to 1, but that's just generally how you would write it. Okay. So the next thing that we might be interested in then is figuring out some information about our random variable. In particular, we might be interested in the expectation of x on the one hand and the variance of x on the other hand. Okay? So the expectation of x and the variance of x. So the expectation of x of a continuous random variable, and in this case with a normal distribution with parameters mu and sigma squared, is going to be given by this integral. The integral from minus infinity to infinity of x times 1 over the square root of 2 pi sigma squared e to the minus a half x minus mu over sigma squared dx. Okay. Now this looks a little bit mean, does this integral? Actually, it's really not that. It's not going to be that difficult to deal with, for the simple reason that we've already kind of done what we need to do in many ways to figure out what we need to do. You can use substitution. You can use integration by substitution here, or you can do, again, the reverse chain rule, whatever you want to call it. I'm not going to go through all of the details of this, but suffice it to say that really this integral is of the form, the integral from, in fact I will put limits in, the integral of t e to the minus t squared. It's in many ways of this kind of form. It's just a little bit messier. Okay, but if you think about how would you integrate this thing and just kind of widen your scope a little bit, then you should be able to figure out an integral, an antiderivative for this thing here. Okay, but it turns out, let me just clear a bit of space again. It turns out that this is just equal to, you fill in the gaps, equal to mu. So, expectation of x is sometimes called the mean. Okay, and what you will find is that often when you're given a normal distribution, you'll be told x is distributed normally with mean mu. And this is not for no reason. Right? There's a good reason for this, because when we calculate the expectation of a normal distribution, it comes out to be mu. So hence the first parameter is often referred to as, funnily enough, the mean. But now we've justified why that's the case. Rather than just saying it's the mean, we've actually shown here why we refer to that parameter as the mean. And similarly, I mean, you can probably guess what's going to happen here, but if we want to calculate the variance of x, we calculate this integral, which is going to take a little bit more work for you to do. Again, I'm not going to go through the details of this. But here you're probably going to need to use integration by parts. So it's going to be x minus mu squared times 1 over the square root of 2 pi sigma squared e to the minus a half x minus mu over sigma squared dx. You're going to need to use some integration by parts. If you're on top of your integration at A level, you can calculate something like this. It looks a bit menacing, but it's really not. It's not too bad at all. Try using substitution maybe. a decent enough substitution. X minus mu maybe. It's maybe a good idea. Or even x minus mu over sigma. Try it out. Okay? Try different things out. I'll leave you to fill in the gaps, but what you'll get is that the variance is equal to sigma squared, and hence the second parameter in our description of our normal distribution is often referred to as the variance. Would you believe it? Okay. But now, again, we've justified why that is. Rather than just saying these parameters are called the mean and the variance, now we know why. Okay, so now we're on a roll now. We're getting some of these details hammered out. Okay. Did I... This, I meant to mention this earlier, actually. This z equals x minus... I can't actually remember if I mentioned this, but maybe at some point along the way you've seen this transformation. Z equals x minus mu over sigma. This can be used to transform just any normal distribution, any normal probability density function into the standard normal probability density function. Okay. So hopefully you've seen that at some point. Okay. So what that means is then, just to spell it out a bit more, if we've got x is distributed normally with parameters mu and sigma squared, then z, which equals x minus mu over sigma, is distributed normally with parameters 0 and 1 squared. Okay, so this transformation takes a normally distributed random variable and transforms it into a standard, a random variable that has a standard normal distribution. Okay, so I've got a few notes here because there's quite a few things that I want to cover, and I want to make sure that I get them all in this video. So what else was there? Oh, we want to have a look at what the graph of f of x looks like. Okay, so just to remind ourselves, f of x equals 1 over square root of 2 pi sigma squared e to the minus a half. Yeah, okay, so x minus mu over sigma squared. Because this is just a function, we want to know what does the graph of this function look like. Okay, now you probably know. I'm pretty sure that you will have been shown what the graph of a probability of a normal distribution looks like. But as you well know, we have techniques. You're shown techniques at A level, analytic techniques involving differentiation and things like this, that will inform you about what the graph of a function looks like. So what we're going to have to do for a little while is suspend our understanding of what the any existing knowledge that we have, and understanding of what the graph of a normal distribution looks like, and pretend that we don't know any of that. And we're going to figure this out from scratch. Okay, again, I'm going to have to miss out some of the finer details. Otherwise, the video is just going to go on forever. But let's have a look at what we get up to. So what we want to do is we want to have a look at... first, we're going to have a look at what happens to the function as it goes out to plus infinity and minus infinity. Okay, so as x approaches plus infinity, and we can do all these in any order, really. The things that I'm about to do, you can do these in... you don't have to do them in this particular order. So as x approaches plus infinity, well, in that case, then we've got x minus... Let's have a look at this x minus mu over sigma. If x gets really, really big, and mu and sigma are finite constants. Okay? So if I've got something, x can just get... no matter how big mu is, no matter how big sigma is, x can just totally eclipse the values of mu and sigma. So as x gets closer to infinity, x minus mu over sigma is just going to approach the value of x. I don't like that. It's just going to approach the value of x. So in other words, the value of e to the minus a half x minus mu over sigma squared is just going to approach the value of e to the minus a half x squared. Okay. So as x gets bigger and bigger, this is just going to approach 0. It's going to approach 0 from above because remember this is a e to the minus a half x squared is always going to be non-negative. It's going to be positive for any finite value of x. So we're going to approach 0 from above. Similarly, as x approaches minus infinity, we're going to get x minus mu over sigma again, just approaches x. E to the minus a half x minus mu over sigma squared approaches again e to the minus a half x squared, which approaches 0 again from above. Okay, so we've got a little bit of information about the behavior of this function. Okay, what about turning points? Okay, so we might want to calculate d by dx of f of x. So I've got this written down actually because I don't want to get this wrong. So it's minus 1 over sigma squared x minus mu times 1 over the square root of 2 pi sigma squared e to the minus a half x minus mu over sigma squared. Okay, so use chain rule to differentiate if you need to. So when is this equal to 0? So setting this equal to 0, we can see that because this is never going to be equal to 0, and in fact this is never going to be equal to 0 either. The only way that d by dx of f of x is going to be equal to 0 is if x minus mu equals 0, which means that x is equal to mu. So we've got a turning point. Is a turning point. And what's the value of f at this turning point? So f of mu is equal to 1 over the square root of 2 pi sigma squared e to the minus a half. Now it's x minus mu, so it's going to be mu minus mu over sigma squared. Well, this is just equal to 1. So we get 1 over square root of 2 pi sigma squared. So this is equal to 1 because mu minus mu is equal to 0. E to the minus a half times 0 squared, e to the 0 is just equal to 1. Okay, so at our turning point, and we don't know whether it's a maximum or a minimum or point of inflection yet. We're going to find that out in a second. F of mu is equal to 1 over 2 pi sigma squared. We can go even further. We can show that the line x equals mu is a line of symmetry. Why so? Let's have a look. So let's consider, again, I've written this down because I don't want to get this wrong. Where did I? Oh yeah. So if we consider f of mu minus a, okay, so we may as well assume that a is greater than 0. F of mu minus a is equal to 1 over the square root of 2 pi sigma squared e to the minus a half. So x is equal to mu minus a. So it's mu minus a plus minus mu over sigma squared, which is equal to 1 over the square root of 2 pi sigma squared e to the minus a half, and what is it? It's minus a over sigma squared, which in turn is equal to 1 over the square root of 2 pi sigma squared e to the minus a half a over sigma squared, which equals 1 over square root of 2 pi sigma squared, e to the minus a half, and it's going to be mu plus a minus mu over sigma squared, which is equal to f of mu plus a. So therefore, x equals mu is a line of symmetry. Okay. So we're building up our picture of this normal distribution, of the graph of this normal distribution. But we're not done with that turning point yet. We need to figure out what kind of a turning point. Now, we might suspect that it's a maximum, but we need to show, right? That's the whole point of having these techniques available to us, is that we use them to show these properties. Okay, so let's have a look. So f primed of x, or d2 f of x by dx squared, whichever you prefer to write. So you're going to have to use, again, product rule and chain rule, because you're going to have to differentiate that function that we had before. So what was it? Minus 1 over sigma squared, x minus mu, times 1 over square root of 2 pi sigma squared, e to the whatever, right? You're going to have to differentiate that again, so that's going to be a product rule and another chain rule, probably. And you get something that looks like minus 1 over sigma squared. I'll leave you to fill in the gaps with this. 1 over the square root of 2 pi sigma squared. E to the minus half x minus mu over sigma squared. Plus 1 over sigma to the power of 4 x minus mu squared, e to the minus a half x minus mu over sigma squared. Ooh. So that's what you should get if my calculations are correct. So when x equals mu, this all reduces to f prime primed of mu equals minus 1 over sigma squared hang on. Times 1 over the square root of 2 pi sigma squared. Because notice that when x is equal to mu, this is going to be equal to 1. This is going to be equal to 0. And therefore all of this is going to be equal to 0. And therefore this is negative. This is going to be less than 0. So what can we conclude? X equals mu is a maximum. And that's second derivative test that we're using there. Second derivative test. Okay. So I'm leaving some things here for you to have a figure out for yourself. But if there is anything that you're not sure about, like I said, just ask the question. Okay, we're still not done. Because what we can have a look at now is what about when f prime primed of x is equal to 0? Okay, so when f prime primed is equal to 0, notice that we can divide through by e to the minus a half. If we set this expression equal to 0, we can divide through by e to the minus a half x minus mu over sigma squared, because this is not going to be 0. It's not going to be equal to 0. But it's a common factor in both of these terms. So what we end up with ultimately is that minus... let me get this right. I think I've missed something out, haven't I? I missed something out in here. There should have been a 1 over square root of 2 pi sigma squared in there. So we can actually divide through by that as well. We can divide through by 1 over 2 pi sigma squared as well. Because again, that's going to be non-zero. So what we end up with is minus 1 over sigma squared plus 1 over sigma to the power of 4 x minus mu squared is equal to 0. Multiply through by sigma to the power of 4, rearrange a little bit, and you're going to get x minus mu squared is equal to sigma squared, and therefore x x minus mu is equal to plus or minus sigma, and therefore x is equal to mu plus or minus sigma. Okay, so what this means is that there's 2 points where the second derivative is equal to 0, but because we know at both of these points that the first derivative is not equal to 0, otherwise it would have shown up in our calculation earlier, what we can deduce then is that x equals mu plus sigma and x equals mu minus sigma are points of inflection. Okay. So I think we've got enough information now to start putting our picture together of what our normal distribution is going to look like. There's not going to be any surprises here, by the way. I'm pretty sure you already know what it looks like. So we've got x here, f of x here. So we've got our this is mu. Okay, this is our line of symmetry. This is not necessarily 0 unless we're dealing with the standard normal distribution. So we've got mu, and remember we've got a maximum here. And what's the value of the maximum? It was 1 over square root of 2 pi sigma squared. Okay. We've got these points mu plus and minus sigma, mu plus sigma, mu minus sigma, and we've got points of inflection there, and the function goes off to it drops down to 0. Okay, it tends towards 0, so we get this kind of picture for our normal distribution, something like that. Okay, which you're probably familiar with, and that's okay. That's it. That gives us a decent enough idea about what our normal distribution is going to look like. So then we can start to potentially calculate probabilities from this. Okay, we wouldn't actually need to know what the graph looks like to start to calculate probabilities. We could have done that before. But it's going to be much easier for us to visualize the various probabilities that we're interested in. Now, there is a bit of a problem when it comes to finding these probabilities, because we're going to have to integrate. Okay, in particular, we're going to have to find the integral. Okay, let me show you first of all how we're going to do this. Again, you probably already know this, but I'm just going to go through it anyway. So if this is, that's not a very straight line, is it? This is our normal distribution. And I would recommend, by the way, that you do get into the habit of drawing a normal distribution when you're dealing with them and you're calculating probabilities. So let's say we want to calculate the probability that so x is distributed normally with parameters mu and sigma squared. So we get something like this. The probability that a is less than or equal to x is less than or equal to b, for example. Okay, A and B could be more or less anywhere. Let's just say that A is here and B is here. Okay, so what we want to do is to find effectively this area. Now we're going to have to find this area by calculating this integral from, not minus A, the integral from A to B of f of x, which is 1 over the square root of 2 pi sigma squared, e to the minus a half x minus mu over sigma squared dx. This is going to be equal to the probability that a is less than or equal to x is less than or equal to b. Problem. We can't calculate this integral. We can't find an antiderivative. So what can we do? The only thing that we can do is to approximate this probability. So maybe you've come across things like trapezium rule or Simpson's rule, maybe, for numerically approximating integrals. Well, we're going to have to resort to something like that to approximate the value of this integral, rather than being able to find its exact value. So that's where the probability statistical tables will come into play. I don't actually have mine to hand anywhere apart from here. Okay, so you'll have some tables that kind of look something like that. Statistical tables. But then you're faced with another problem. The statistical tables only give probabilities that are relevant to the standard normal distribution. And not only that, they only give some of the probabilities. So you've got a bit of work to do, potentially. I'm not going to go through all of this, but in this video, because it's already nearly an hour long already. But what you've got to do, if you've got just a normal distribution that's not necessarily a standard normal distribution, you've got to effectively transform that probability that's expressed in terms of x. You've got to transform it into a probability in terms of z, a standard, a random variable that follows a standard normal distribution. And then you're going to have to use properties like the line of symmetry, reflectional symmetry, and things like this to help you calculate certain probabilities. Now, I'm sure you've been told about how to do this. Get familiar with doing this. Even though it seems like an archaic thing to do now, I would recommend that you get used to using statistical tables for calculating normal probabilities, rather than just relying on your calculator, for the simple reason that you will get a better understanding of how the normal distribution works. I'm not saying that you have to do it for all eternity, but just for a while, rather than just getting your calculator to calculate everything for you, actually use the statistical tables. Do things manually, because you will get a better understanding of how a normal distribution works and the various relationships between the standard normal distribution and other normal distributions, and how certain probabilities are related to each other and things like this. And this is important. A lot of people really overlook this. All they're bothered about is just getting the answer, even if that just means just plugging some numbers into a calculator and just taking whatever number pops out. If you really want to get ahead with your mathematics, you're going to have to put some work in. Okay, once you're familiar, once you've really developed a certain level of confidence and knowledge and understanding of these relationships and things like that, by all means use your calculator. It's not because I'm just trying to be old-fashioned. There is a benefit to not using a calculator for a while, at least. Not just with normal distributions, but with other things as well. For example, calculating binomial coefficients and things like that. Because if you overuse your calculator, you don't give yourself the practice that you need with spotting certain patterns, and your understanding really lags behind. Okay, so we're pretty much coming up to the end of the video now, and there's only really one thing that I want to mention, which I'm not going to go into much detail with in this video because it's already been long enough, which is the distribution of what's called the sample mean. Okay, so what is the sample mean? If we've got random variables x1, x2, x3, x4, up to xn, and the xi's are all distributed normally with parameters mu and sigma squared. So it's what's called identically distributed. And not only that, they're independent. So this is sometimes abbreviated to IID. Independent and identically distributed. So if x1 to xn are independent and identically distributed, and for now we're going to assume that each of them are distributed with this particular normal distribution, mu and sigma squared, then x bar, which is the random variable 1 over n times the sum of xi from I equals 1 to n, is distributed normally with parameters mu and sigma squared over n. Okay, this is called the central limit theorem. This is not the central limit theorem in its full force. This is a particular version of the central limit theorem. Okay, so central limit theorem. The central limit theorem is much more general than this. Generally speaking, what you can have is n IID random variables, independent and identically distributed, and provided that the distribution that they follow, it doesn't necessarily have to be continuous or discrete. As long as it's got a finite mean and a finite variance, then what you can say is that the sample mean, x bar, which is this thing here, the sample mean, is not necessarily going to be exactly normally distributed, but it's going to be approximately normally distributed. Okay, but if we've got x1 to xn are all normally distributed, independent, identically distributed, then the sample mean based on that sample has a normal distribution with parameters mu and sigma squared over n. Okay, and also you might have seen the transformation z equals x bar minus mu over sigma over the square root of n, for example, for taking the sample mean. So just like before, we had z equals x minus mu over sigma, which takes a normal distribution, a random variable that's got a normal distribution, and transforms it into a random variable that has a standard normal distribution. This does exactly the same thing. X bar, sample mean, is a random variable. Okay, it's got a probability distribution. So because it's a random variable with a normal distribution, we can transform it into, via this transformation, x bar minus mu over sigma over root n, into a random variable with the standard normal distribution. So that's called the central limit theorem. That comes into A-level hypothesis testing. I'll do another video on that at some point, but I just thought I'd bring it up at the end of this video. Okay, so I think that's pretty much it for this video. If there is anything that you want me to explain in more detail, please let me know. I've already included a lot in this video, but feel free to ask any further questions that you need to ask. So, without further ado, thank you for watching. If you made it right to the end of this video, then congratulations. Very well done. I will look forward to seeing you in the next video. Thank you very much for watching.